In this section, we're going to talk about implicit differentiation. Now, up to this point, our functions have been written in explicit form, and all that means is that they are solved for y. It's explicitly stated what y is equal to. In this case, we're going to talk about functions which are in implicit form, meaning they're not necessarily written as a function. So, for example, if we have y equals 1 over x, which is the same thing as x to the negative 1, that's the same exact thing as if we had written x times y equals 1. It's just we've divided by x on the left to get y by itself. And you can find the derivative of that function in either form. So I kind of want to recap what we had talked about before. When you're differentiating an expression with respect to x, if the variable that you see here is not an x, then you have to multiply by that variable's derivative on the outside. You have to use the chain rule with it. So in this case, because we have the same variable here, it's just straightforward. The derivative with respect to x of x to the fourth is going to be 4x cubed. Now, look at the next example. We've got an x and a y. So since these are different variables, we have to use the chain rule. So what that means is when I take the derivative, I'm going to have 4y cubed, because I take the derivative of y to the fourth, and then I multiply it by y prime, or if you want to make it a little bit more convenient for the work we're going to do, we're going to call that dy over dx. Remember, y prime and dy over dx mean the same exact thing. Now, sometimes with implicit equations or implicit functions, you actually have both of these in the same step. So I've got the derivative with respect to x of x squared plus y cubed. Remember, I can break that up as the derivative with respect to x of x squared plus the derivative with respect to x of y cubed. Now in this first example, my variables match, so we're good with that. That's just going to be 2x and then we're done. But in the second part here, my variables do not match, so that means that I have to use the chain rule. So this is going to be 3y squared times dy over dx, and that would be my answer here. Now we're going to extend that idea to be able to do implicit differentiation on an equation with respect to x. So the difference here is that instead of just taking the derivative with respect to x of an expression, we're actually going to be doing this for a whole equation, and then we're going to be solving for dy dx. So we differentiate both sides of the equation with respect to x. We collect all the terms that have dy over dx on the left side of the equation and anything else on the right. We'll factor out the dy over dx, and then we will solve for it. So let's look at a simple example. I have the derivative with respect to x, or derivative of y with respect to x, and my equation is x squared plus y squared equals 1. So I'm going to start by taking the derivative with respect to x of both sides of the equation. And on the left, I'm going to split it up as to the derivative with respect to x of x squared plus the derivative with respect to x of y squared, and that's going to be equal to the derivative with respect to x of 1. So we're going to take care of the low-hanging fruit first. We know the derivative of a constant is just a 0, so the right-hand side of this is 0. Now coming over here you'll notice your variables match, so that's just going to be 2x. But here you notice your variables don't match, so that's going to be 2y times dy over dx. Now my goal is to get dy over dx by itself, so I'm going to start by taking that negative 2 or that 2x and subtract it from both sides. So I get that 2y dy over dx equals negative 2x. And then to solve for dy over dx here, which is what I want, I'm going to divide by 2y. So I get that my answer is dy over dx is equal to negative 2x over 2y, or dy over dx equals negative x over y. And that is my answer. And that is how it's done. That is my answer. Now we're going to do this again for this example. So I'm going to take the derivative with respect to x of both sides of the equation. And then I'm going to split it up. So I've got the derivative with respect to x of x squared plus the derivative with respect to x of y squared. equals the derivative with respect to x of x plus the derivative with respect to x of 3. And where my variables match, it's just going to be straightforward. Where my variables don't match, it's going to be like that. So the right-hand side is a little more simple. This will be 1 plus 0. On the left, I'm going to have 2x plus 2y times dy over dx. So again, this is what I'm trying to solve for. So I'm going to subtract the 2x term. So I get 2y dy over dx equals 1 minus 2x. And then I'm going to divide by 2y. So I get that dy over dx equals 1 minus 2x divided by 2y. Sometimes your answers will have a y in it. There's nothing wrong with that. Again, we're going to take the derivative with respect to x of both sides. So that's x cubed plus y cubed on the left, and the derivative with respect to x of 2y squared plus 2x on the right. So I'll split that up. And then I'm going to check the variables match on this term and on this term. And they do not on this term and on this term. So this one will just be 3x squared. This one will have to be 3y squared times dy over dx. Over here we're going to have 4y times dy over dx. And we're just going to have a 2 at the end. Now I want to solve for the dy over dx, and notice I have a dy over dx on both sides of the equation. So I am going to have to move some things around a little bit. I'm going to move the 3x squared to the right, so I subtract that, and I'm going to move the 4y dy dx to the left. And there's no analog that you actually divide, or that you actually line it up with here. I'm just kind of putting it on the side where it goes. So I have 3y squared dy over dx minus 4y dy over dx equals 2 minus 3x squared. And on the left, I'm going to factor out a dy over dx. Now yes, I know I could factor out y dy over dx, but I'm not going to do that because I want to get dy over dx by itself. So I'm just going to factor out that. So this is what we're trying to solve for. So I'm just going to divide by what it's being multiplied by. So I get dy over dx equals 2 minus 3x squared divided by 3y squared minus 4y, and nothing will simplify, so that is my answer. Now taking a look at this one, we're going to start out exactly the same way. The derivative with respect to x of xy is going to be equal to the derivative with respect to x of 6. Now the thing about this one is, when we do this by implicit differentiation, we're going to need to use the product rule because we have x times y. So we're going to need to use the product rule here. We're going to have f equal to x, and we're going to have g equal to y. Now when you go to find f prime, those variables are going to match. So that's just going to be 1. But when you go to find g prime, you're taking the derivative with respect to x of y. So this is actually going to be dy over dx. So for the product rule here, this is going to be fg prime plus gf prime. So that'll be x times dy over dx plus y times 1. And then, of course, the derivative with respect to x of 6 is just 0. So again, I'm trying to get dy over dx by itself, so I'm going to subtract y. I get x dy over dx equals negative y. And then I'm going to divide by x. So I get dy over dx equals negative y over x. Now from here, you could leave it like this. There's nothing wrong with that. But since you do know that xy equals 6, and you could solve it for y, we know y is 6 over x, we can make that negative 6 over x divided by x, or negative 6 over x squared. So sometimes you'll be able to do that. If you can clearly solve for y, you can plug it back in. Sometimes you might not be able to do that. Now you could actually do this derivative explicitly as well. If you take the xy equals 6 and go ahead and solve it for that, then that is 6x to the negative 1. So dy over dx would be 6 times negative 1 times x to the negative 2, or negative 6 over x squared. So you can see either way you're going to get the same answer. The only time when you would absolutely have to do this product rule is if the xy is a term that's in another equation that has maybe more y terms and you can't exactly solve it for y. Now you can absolutely find equations of tangent lines to graphs of equations that are written in implicit form, and that's usually the reason why we'd actually want to do this. So if I want to find the equation of the line tangent to the graph of y cubed minus x squared equals 4, I am going to need dy over dx in order to find my slope. So I'm going to take the derivative with respect to x of y cubed minus x squared and the derivative with respect to x of 4. So that's the derivative of y cubed minus the derivative of x squared equals the derivative of 4. And again, I have a match here and a mismatch here. So that's going to be 3y squared dy over dx minus 2x equals 0. I would add the 2x. I'd get 3y squared dy over dx equals 2x. And I divide by the y squared, or sorry, the 3y squared. So I get dy over dx equals 2x over 3y squared. Now, I need to find my slope. So we know that the slope is the derivative of y with respect to x at the point that we were given. And the point we were given was 2, 2. So this is my x and this is my y. This is a little different because we haven't ever plugged a y in to a slope of a tangent line before. But our formula is 2x over 3y squared. So we need the y. We're going to plug that in. So that'll be 2 times 2 divided by 3 times 2 squared. Or I get that my formula is, or my slope for my formula is 1/3. So y minus 2 is going to be 1/3 times x minus 2. And if you simplify that down, you get that y is 1/3 x plus 4/3. I'll let you take care of that. You can even do it with some interesting functions like this. So this says sine of y equals x, and this is actually a function of y. So it's kind of like the sine function, or the sine wave turned on its side. But it works exactly the same. So we would take the derivative with respect to x of sine of y equals the derivative with respect to x of x. So again, I have a match here and I have a mismatch here. So this is going to be cosine of y, because that's the derivative of sine, times dy over dx, and this is going to be 1. So when I divide by cosine of y, I get the derivative of y with respect to x is equal to 1 over the cosine of y, or if you want to think of it that way, it's actually secant of y. So the slope, remember this is x, this is y, m is equal to the secant of pi, or 1 over cosine of pi, which is 1 over negative 1 according to your unit circle. Remember, pi is out here, so that's x equals negative 1. So that slope is negative 1. So y minus pi is going to be negative 1 times x minus 0 according to my point slope form. So y minus pi is negative x, and if I add pi, I get that y equals negative x plus pi. So this is a straight line with a slope of negative 1 and a y-intercept of pi.